Hi, in today's video we're going to talk about the wave properties of light. In this video we're going to discuss the important features of a wave. We're going to define a few important terms. We'll tell how an electromagnetic wave's frequency and wavelength are related. We'll introduce the various regions of the electromagnetic spectrum, and we'll work 3 examples showing how to apply these concepts. Light is an electromagnetic wave. When you think about an electromagnetic wave, you can think about a wave that has 2 components. The first is an electric component which moves along, and you'll see here this wave is moving in this direction. And the electric component is shown in the yellow plane. There would be an orthogonal magnetic component which is shown here in the blue plane, and it would move along oscillating in this direction here. So these waves are perpendicular to one another. We use the letter c to refer to the speed of light. The speed of light has been determined to be 2.998 times 10 to the 8 meters per second. Before we go any further, it'd be helpful to review a few of the important features of a wave. Let's define a few important terms. We'll define crest, trough, wavelength, and amplitude. The crest are these high points right here. The trough are the low points. These two will be equally separated from the origin, such that this distance here will be equal to that distance there. That distance is known as the amplitude. So the amplitude is the height of a crest or the depth of a trough. The next term we need to define is the wavelength. The wavelength is the distance that separates one trough from one trough, or one crest from one crest. Now that I have this red wave on the screen, I'm going to superimpose a blue wave on it. Notice that these 2 waves have the same amplitude, in that they have the same height that they achieve from the origin. But they have much different wavelength. Notice the red wave completes a wave cycle in this distance here, say from here to here, whereas the wavelength of the blue wave is much shorter distance. So the 2 waves have the same amplitude, but they have much different wavelengths. So let's talk a little bit more about the wavelength. The wavelength, as we've said, is the distance between 2 troughs, 2 crests, or 2 other identical points on the wave. So we've said we could measure here to here, or here to here. As long as we pick out the 2 points on the wave that are the same, it doesn't matter. Lambda is the symbol that we use to refer to wavelength. That's this symbol here. And wavelength is an actual length, and so it's going to have units of meters, centimeters, micrometers, or some other distance, but it is a length. Let's talk a little bit about frequency. Frequency refers to the number of wave cycles completed per second. Frequency is referred to using the symbol nu, which looks like a cursive V. Frequency has units of per second or hertz. You can use hertz and per second interchangeably. Now to see what frequency looks like here, imagine yourselves that you are traveling on a little red dot, traveling along 2 different roller coasters. And if we watch here, we see that these 2 dots move along the x direction in the same speed, in that it takes 3 seconds for them to move all the way to the right of the screen. But notice that the bottom dot must go over many more peaks and valleys in its progress. So we can calculate the frequency of the top wave by noting that it completes 3 wave cycles over a 3-second time interval. So that's 3 cycles per 3 seconds, or 1 Hertz. The bottom wave completes 12 wave cycles over the same time interval, or 12 cycles per 3 seconds, or 4 Hertz, or 4 per second. We notice that there is a relationship between frequency and wavelength. We've seen that when the wavelength decreases, the frequency increases by the same factor. Remember that we decreased the wavelength by a factor of 4. That means that we increased the frequency by the same factor. The same thing is true for light. The frequency and wavelength of an electromagnetic wave are inversely proportional to one another and can be found using this equation here, C equals lambda nu. This is a very important result. Remember, C is the speed of light, 2.998 times 10 to the 8 meters per second. Let's try an example and apply what we've learned. Suppose a traffic light emits a light which has a wavelength of 650 nanometers. Use the speed of light to find the frequency of the light. Okay, before we begin this problem, let's plan a course of action. We're given the wavelength of a light, 650 nanometers. We're also told that we can use the speed of light and that we're asked to find the frequency of this light source. So let's use our new equation that we've just learned, C equals lambda nu, and let's use the speed of light and solve for frequency. First, we know we're going to use C is equal to lambda nu. This equation relates the wavelength of an electromagnetic wave to its frequency. Then we'll rearrange the equation to solve for the variable that we're looking for. We wanted to, and we were asked to solve for the frequency. Next, all we have to do is plug in the appropriate speed of light in for C and the wavelength that we are given, 650 nanometers, in for lambda. As we plug in our values, we'll need to make sure to use the speed of light, of course, is given in meters per second, so we'll need to make sure that we use the wavelength also in meters. So we need to use 650 times 10 to the minus 9 meters. When we do this, we get 4.6 times 10 to the 14 per second, or 4.6 times 10 to the 14 Hertz. Notice how the units of meter here cancel out to give me the units of per second, which is exactly the right kind of units I should have if I'm trying to find frequency. Let's try another example. In this example, I'm asked to find the wavelength of a cell phone signal whose frequency is 1000 megahertz. This example is very similar to the previous one, except I'm working it in reverse. This time I'm given the frequency and I'm asked to find the wavelength. I'm going to use the same equation I did last time and the speed of light. So I start out with the same equation, C equals lambda nu. I rearrange it solving for the wavelength. And when I plug everything in here, I plug the frequency on the bottom, and the units of per second cancel out nicely to give me units of meters, meaning my final answer, rounded to one significant figure, is 0.3 meters. This is my wavelength. So in summary, we've seen that we can use this equation, C equals lambda nu, to either solve for a frequency or a wavelength when given the other. Let's pause for a minute and think about our last two answers. We found that the stoplight, which had a fairly short wavelength of 650 nanometers, had a comparatively high frequency when compared to the cell phone that had a much longer wavelength. So we can clearly see the inverse relationship between the wavelength and the frequency. Notice if I take the product of the frequency and the wavelength, I will always, when multiply these guys together, I will always get C. Let's talk just for a minute about the electromagnetic spectrum. The electromagnetic spectrum consists of all the different types of electromagnetic radiation, and visible light is just one tiny sliver of that spectrum. We can see here on one end of the spectrum we have our red and our orange colors, and then down there at the shorter wavelengths we have our purples and our blues. But our eyes can conceive of only these portions here between 400 nanometers and 650 nanometers. That's it. But there's a lot else out there that our eyes can't pick up on, like the ultraviolet radiation, X-rays, and gamma rays. These are types of radiation that have shorter wavelengths than what our eyes can pick up on. If we move into the longer wavelength portion of the spectrum, we see things like infrared, microwave, and radio and TV waves. Let's try another example. This is our last one. In this question, we're asked to find the type of electromagnetic radiation from the ones listed that has the highest frequency. Our choices are radio, X-rays, infrared, or microwaves. To answer this question, we need to recognize that there is a link between the wavelength and the frequency. And we'll use C equals lambda nu to answer this question. Let's refer back to the electromagnetic spectrum that we just talked about and identify the 4 regions that we were asked to choose between. They were X-rays, infrared, microwave, radio, and TV. We were asked to find the one which has the highest frequency. The highest frequency is going to be found when our wavelength is shortest. So, if the wavelength increases in this direction, that means the frequency is going to increase in this direction. So the highest frequency side of the electromagnetic spectrum is down here where your UV, your X-rays, and your gamma rays are. So the choice would be X-rays. That would be the answer to the question. In conclusion, today's video talked about light as an electromagnetic wave. We defined important terms, and we solved for frequency and wavelength using the important equation C equals lambda nu. I hope you enjoyed watching the video, and please let me know if you have any questions in office hours or consult your textbook. Thanks.